Alrighty, stat students. Today we're going to be looking at section 1.2. So in 1.1 we talked about categorical data quite a bit, and I've got a handout today for you all with some basic vocabulary terms kind of for the whole chapter. It's something I probably should have gave to you before we started section 1.1, but it's okay. I just want to make sure you have it now. So you'll have an attachment also that's got something in there for it's got some basic vocabulary about categorical versus quantitative data. And so today we're kind of shifting gears and we're going to talk a little bit more about quantitative data. And we're going to talk about displaying quantitative data with graphs. So we talked about displaying or visualizing and analyzing categorical data in the last section. So now we're going to focus on quantitative data. All right, so our learning objectives for this will be make and interpret dot plots and stem plots of quantitative data, describe the overall pattern of a distribution and identify any outliers, identify the shape of a distribution, which is going to be very key, setting groundwork here for everything we do and from here on out. And we're also going to make and interpret histograms of quantitative data and compare distributions of quantitative data. So we'll compare two different distributions there. All right, so dot plots is one of the simplest ways to graph and construct and interpret. One of the simplest graphs to construct and interpret. Each data value is shown as a dot above its location on a number line. So how to make a dot plot? Well, you draw a horizontal axis, a number line, and you label it with the variable name. And you always want to make it from, your lowest value up to your highest value. Basically, you want to make sure that those do fall on the number line that you draw. You can scale the number line however you want to. But you scale it from your minimum to your maximum value, and you mark a dot above the location on the horizontal axis corresponding to each data value in the set. So here's a set of data and the dot plot that goes with it. So you've got all these numbers here. You got 0 and you got some other numbers here all the way up to 14. And so at 0, since there's only one 0 in this data set, I put one dot there. There's 1, 2, 3, 4 ones, so I put 4 dots at 1. Even though 1's not labeled, we go 0 because it's going, being scaled by 2's here. 1 is going to be halfway in between 0 and 2, obviously. At 2, there's 5 2's. You go through and you count them. You can make sure there's 5 3's and then everything. And so you do all that. You plot all the dots, and then you got your dot plot. All right, so we can examine the distribution of a quantitative variable. So the purpose of a graph is to help us understand the data. After making a graph, we ask ourselves, what do we see here? What do we truly see in this? Well, if in any graph, look for an overall pattern or, any kind of striking departure from the pattern. So we want to be able to describe three things here. We want to describe the overall pattern by its shape, its center, and its spread. Notice that individual values that fall outside of the overall pattern, these departures are called outliers. So we're looking for values that maybe, if we have most all of our values on one end of this number line, but there's one number way off over here to the far outside, that's called an outlier. So anything that deviates from that overall pattern is that. So we always want to, don't forget socks. So we're looking for being able to do that. So we always want to make sure that we look for the shape, the center, and the spread. Now, when describing a distribution shape, concentrate on the main features. Look for rough symmetry or clear skewness. A graph that's symmetrical is basically going to be a mirror image of itself. So it's going to be able to fold over onto itself. That means you have kind of a middle, usually kind of a hump sort of, or something like that, but not necessarily. You could have, if all your dot plot looks kind of like a rectangle of dots, then that would be symmetrical as well. But basically, it would fold over on itself. There's no major value off to the end or anything like that. There tends to not be a lot of outliers, or if there are outliers, there's the same number of outliers on both sides of the distribution. If it's roughly symmetrical. A distribution that's skewed right basically, if it's right skewed, that means the right side of the graph is much longer than the left side. So you're going to see that basically when you're looking at the shape of it here. So here's some examples here that helps a whole lot here with this. So you've got, if it's skewed to the right, basically you have values on the right side that stretch out the distribution really long out to the right. So basically it bottoms out to the right, but your value's off to the right, you have some outliers to the right, basically, is what is happening there. Whereas left skewed just means that the left side is much longer than the right side. You have more values towards the right end of the graph, so it's left skewed because you've got some values to the left, but it's stretching it out really long to reach those values out that way. And then symmetric, here's a graph that's roughly symmetrical, and it's not exactly perfect, it's roughly symmetric. All right, so when comparing the distributions, some of the most interesting statistics questions involve comparing two or more groups. Always discuss shape, center, spread, and possible outliers. That's what SOX stands for. Shape, outliers, center, and spread. Okay, that's what it means by SOX. I did not explain that here a minute ago. Sorry about that. So you're always going to discuss shape, center, spread, and possible outliers whenever you compare distributions of a quantitative variable. So every time you're asked to compare two distributions, SOX, shape, outliers, center, spread. Okay. So basically, we're looking at these two distributions here. Household size down here at the bottom. And I know this little, let me see. There we go. We moved that out of the way. All right. So household size versus, we're looking at household size, and it looks like the UK and then versus South Africa. All right, so we want to compare these distributions. So we don't want to forget, So if we're looking to compare these two distributions, we can see that roughly they're kind of centered at the same value, around 5, but there's less of a spread with the UK versus South Africa. South Africa is a bit more skewed to the right because there's some outliers out here. So it's a bit more skewed to the right, whereas the UK is a bit more symmetric, or roughly symmetric. So we've discussed the shapes, we've discussed the centers, we've discussed the spread, and we've discussed the outliers. It doesn't seem like the UK has any outliers here. But South Africa does. So, all right. Stem plots. Another simple graphical display for a small data set is a stem plot, also sometimes called a stem and leaf plot. Stem and plots give us a quick picture of the distribution while including the actual numerical values. How do we make it? Well, we separate each observation into a stem, all but the final digit, and the leaf, the final digit. The stem is all the digits in the number except for the final digit in that number. So if we're talking about 175, 17 would be the stem, and 5 would be the leaf. The final digit in the number would be the leaf. We write all the possible stems down from smallest to largest in a vertical column and draw a vertical line to the right of the column. And then we write each leaf in the row to the right of its stem. And we arrange the leaves in increasing order out from the stem. Provide a key that explains in context what the stems and leaves represent. So this data right here represents the responses of 20 female AP statistics students to the question, how many pairs of shoes do you have? Construct a stem plot. So you've got the number of pairs of shoes, okay, that you own. And so now what you're going to do is you're going to take this data. So all the stems that we're looking at here, it looks like that the lowest number we're dealing with is at least in the teens. So 13, I think. I don't see one lower than 13. See 13, 15, 19. So that would be our first stem. And then it looks like the biggest number that we've got here is 57 maybe. It looks like, yeah. So the biggest stem is going to be 5. And then we start listing, we add the leaves. So you've got 9, 3, 3, and 5, whatever. But you need to order them. there's no reason to even do it this way. The reason why they did it that way is because they were going through, I think, horizontally here and putting them in the order that they appear in the table. But you always want to put them in order, like put the numbers in order. And this is probably one of those things where you would just want to check off. If you're making one of these by hand, which you're going to have to, what I would do, as you're putting numbers into this, I would just go and find the smallest number with that stem, 1. So it was 13. So the leaf is 3. The final digit in the number is the leaf. The first number, all the numbers before it is the stem. So all of these, so I would do it, I'd go through and I'd find that. And then I would just kind of like mark it off, like maybe with a little check or whatever right next to that point. So I know I've used that one. Find any other 13s, then go up to the next number, which is 15, then up to the next number, which is 19. And I just kind of would mark them off as you go through there. You order those, and then remember that 49 represents a female student who reported having 49 pairs of shoes. You want to provide a key explaining what exactly your stem plot represents. What exactly? Give an example of a stem and a leaf in this plot and explain what that means in the context of the problem. So that's why they're saying it represents a female student who reported 49 pairs of shoes, because the context of the problem was asking female AP Stats students how many pairs of shoes they have. All right, so when data values are bunched up, we can get a better picture of the distribution by splitting stems. Two distributions of the same quantitative variable can be compared using a back-to-back stem plot with common stems. So here we got males and versus females. We split the stems. So basically we put the stems down the middle, and then we put the leaves off to the sides. Okay? And so on one side we do males, and on one side we do females. And we just represent that this means a student who reported having 49 shoes, because now we're asking males. Now notice that the male distribution is a bit more skewed to the right, whereas the female distribution is a bit more roughly symmetric, sort of, maybe slightly skewed to the right, but really much less skewed to the right than the males, which makes sense. Of what that's basically saying is that for the males, it means that they have less pairs of shoes, But you do have, somebody that had, you do have some guys had, 35 and 38 pairs of shoes. So you never know. To each their own. All right, quantitative variables, they often take many values. A graph of a distribution may be clearer if nearby values are grouped together. The most common graph of the distribution of one quantitative variable is a histogram. How do we make that? We divide the range of data into classes of equal width. We find the count or frequency or percent relative frequency of individuals in each class. We label in a scalar axes and draw the histogram. The height of the bar equals its frequency. Adjacent bars should touch unless a class contains no individuals. So we've got this table here represents data on the percent of residents from each state who were born outside of the U.S. So you've got your class here 0 to less than 5. 0 to less than 5, 5 to less than 10, 10 to less than 15, 15 to less than 20, and so on and so forth here. And you got your counts there. So total is 50. So we've got all 50 states represented here. So we can have the number of states and the percent of foreign-born citizens. And so we do a class from 0 to 5. That was 20. So we draw a bar up to 20. And then we can see that this looks very roughly right skewed. Okay, because you've got a tail on the end of this. It's almost like if you draw a curve over the bars, touching just the corners right here, you can see that it's stretching out to the right. That's right skewed. So the graph's going to be right skewed for that. But basically, this is kind of like a bar graph, but your bars are touching now. Remember, bars didn't touch on a bar graph. This is a histogram, though. Don't get it confused with the bar graph. Histogram, the bars do touch. I mentioned that there was something else where the bars do touch. Here it is, histogram. So there's several cautions based on common mistakes students make with histograms. Don't confuse histograms and bar graphs. That's what I just talked about. Don't use counts in a frequency table or percents in a relative frequency table as data. Use percents instead of counts on the vertical axis when comparing distributions with different numbers of observations. And just because a graph looks nice, it's not necessarily a meaningful display of data. And there's our summary of our learning objectives for this section. You'll have some homework problems to look at. Hopefully this has been helpful to you, and hopefully if you have any questions, let me know always.